to the 183rd session of the AI Safety Reading Group. This is the second part of If I Were a Well-Intentioned AI. Last time, we covered what it would be like to be an AI who understood Goodhart's law and was well-intentioned enough to try and overcome it. We examined how you would, if you were an AI, go about dealing with it if you were an image classifier. We found that there's a few techniques and strategies that you would be able to replicate. A broad concept you might replicate would be inverse reward design. A strategy might be randomizing your defenses against an adversarial attacker. A technique might be using background versus semantics to find the right features. But without more info on human preferences, we can't improve on that much.
Can I interrupt you for a moment? Can you please make the slide full screen?
Is that better?
Yeah, that's better. Thank you.
Now, this time we're going to be covering what happens if an AI can act in the world, and we'll investigate a few of the types of value functions that give rise to problematic behaviors. So when you're acting in the world, that substantially complicates the situation, but it gives you more info to work with. You'll find that there are preferences for which agent AIs can behave in a Goodhart-like fashion, but for the people who are designing the AI, that's not a problem. They want the Goodhart-like behavior. The reason we usually worry about Goodhart-like behavior is because our preferences are complex and they may be very unlikely from the AI's point of view. We tend to have diminishing returns, negative trade-offs between different people's values, and it may just be that optimizing for our true value is very difficult compared to others. But if AIU understood this, you would be able to avoid a lot of Goodhart-like behavior. So, in this article, Stuart Armstrong gives the example of an AI trying to find its way through a maze. In the training, the AI encounters only red doors. So the AI will be put inside a maze, it will find its way to a red door, and the training session will end. It will get its reward. But unfortunately, like last time, your training does not prepare you for the tough decisions of the real world. You encountered a red window and a blue door, and you don't know which to go to. Based off your training, you could conclude that the humans either meant go to a red thing, a door, or go to a red door. But there's no red door. So here we can discount that possibility safely. If you go to the red thing first, you'll notice that the scenario doesn't end. So perhaps you'll update beliefs and say, okay, I need to go to the door instead of the red thing. Going to the door, you realize that the scenario still doesn't end. So you need to consider that perhaps the humans want you to just stay at some place forever. So either stay at a red thing or stay at a door, and you get continually rewarded. Now, supposing that those are your only two options, then if AIU were to ask your creator, who either wants you to stay by a door forever, or stay by a red thing forever, if they asked their creator whether or not they are suppose you know that your creator, Stuart, either wants you to stay by a red door, a red thing, or by a door. if you said, look, I think you're either a door maximizer or a red thing maximizer, should I just maximize whichever utility I find most likely to be yours? The answer is a resounding yes. Stewart says if AIU is unbiased and finds that it's more likely I'm a door maximizer, standing by the door forever is optimal. Vice versa for if I am a red object maximizer. The point is that given these utility functions, if you believe the AI is unbiased as to whichever one it thinks is most likely, then even if, say, for example, you want the AI to stand by a door forever, and the AI says, I will stand by the door forever with probability P, and I will stand by the red thing forever with probability 1 minus P, that will maximize your expected utility as the creator. Why? Well, in this scenario, the utility we get from going from one thing to another, from the red object to the door, is 0. So essentially, we're incurring an opportunity cost in going between one object to another. So just provided the creator doesn't know what probabilities the AI is assigning for standing next to a red thing or standing next to a door forever, the optimal policy should be of the form, just go and stand in a place forever. I apologize if that was a bit confusing. Now, Stewart goes on to say that in more complicated scenarios, you're going to have a great deal more utility functions that are plausible, and you need to be able to ask your creator some questions to cut down the space of functions. So he refers to a paper where they consider some space of possible reward functions has some volume phi, and the true reward function that you can't really specify easily is this red dot here in the left-hand picture. Now the gray picture, the middle picture has a gray area which sort of represents irreducible uncertainty in the reward function. We've encountered this before, I think in one of Rohin Shah's papers, where he mentions that you cannot fix a utility function from a given policy. No matter what a human behaves like, there is no unique utility function which you can assign them. So there's some irreducible uncertainty in the space of reward functions that's possible. But the AI can still ask some questions and narrow the space down, which is what's going on in the third image. So the point of this image is that you are able to get within an arbitrary accuracy of the ideal reward function up to irreducible uncertainty in a certain number of steps. This steps is bounded, it doesn't increase too rapidly, so asking queries is not in principle too hard. There are some relatively efficient algorithms existing. But you might ask that, why does it still feel very wrong that AIU happens to be standing in one place forever? Looking at that situation, we think, there's something very wrong there. So why did the example feel wrong? As Stewart explains, it's because we have some implicit beliefs about our values. We expect that the true values we hold are hard to optimize. They are penalized in probability from the AI's point of view. Our values might be extremely complex and fragile. They may have diminishing returns, or it could be that we have some contradictory values, so there'll be negative trade-offs. And of course, there is one final element, which is to do with regression. In this case, It's called predictable disappointment, and it's referenced a few times. I believe a common article that's referred to is called the optimizer's curse. Essentially, it says that if you construct some prediction for the true reward given a proxy, you will usually tend to overestimate the reward you'll get based off the proxy. This is because if, for example, you look at a data set, you see that X and Y, which are the proxy and the true reward, are correlated, but near the most extreme section for the proxy value, we see that the regression starts to break apart, and it is no longer a good predictor of what reward we actually expect. This kind of predictor we use is usually called maximum likelihood. It's quite common in machine learning. It's basically a type of Bayesian estimation of what should occur based off the maximum likelihood is like Bayesian regression in a way, except it puts no preference for what kind of parameters your model should use. This results in models that focus mostly on the bulk of the data set doing well, but models that discard the edges, these bits here where the regression comes apart, they're not given much weighting by the maximum likelihood method. Bayesian regression can overcome this in certain instances, and it tends to avoid this predictable disappointment here. So you can see the purple line, which is the Bayesian regression, is at a much shallower angle. From this, we see that we are much less often at the extreme values of the proxy to get a prediction that's too high. So from this point onwards, we'll just be assuming that whatever our AI is doing, it's using Bayesian methods with a relatively informative prior. So here's one of the interesting sections. So suppose AI knows their creator, your creator, is either a door maximizer or a red object maximizer, but their rate of returns for how long you stay next to a door or next to a red object decreases with time. There are diminishing returns. This makes a substantial difference to the behavior of the AI. If the rewards begin to drop off rapidly enough, then eventually, if you stay there too long, then staying one more time step will result in a very minuscule increase in your reward. This will get smaller and smaller and smaller. In this graph, you can see that this is plotted as the derivative of the value. As time goes on, as the more time you spend standing next to a door or next to a red object, you get less and less out of it for each extra turn. Eventually, this will become so small that your expected utility will say, okay, now you should switch over to the other object. You will get a slightly better rate of returns, even though it might be less likely to be the true reward function. This requires sufficiently fast enough. This requires the rewards to drop off sufficiently fast enough. If they decrease, for example, like 1 over the logarithm of the number of steps you've stayed next to the object, then the behavior is quite bizarre. the AI will determine that the optimal policy is to switch between objects, but only after it stays at one for infinitely long, and then it switches to another, which is rather useless to its human creators. So diminishing returns can prevent this Goodhart-like behavior we saw in the maze and get AIs to swap between one location and another. So that's one way we can deal with Goodhart's law. Another case is that you may encounter some very bizarre situations when attempting to optimize value functions. Say, for example, you're playing a game and you are driving around a track. There's a small circle where if you repeatedly loop around, you can get infinitely high rewards. This kind of perverse behavior makes it the most rewarding option to pursue. Obviously, the humans would not wish for this if they tell. This is quite a common problem. It's the usual extremal Goodhart situation. Or it may just be that there's a lot of low-hanging fruit of different utility functions that are very easy to optimize compared to the true reward function, true utility, and the AI will just maximize that collection of utilities. How can you as an AI possibly deal with that if you know about extremal Goodharting? Well, one way is by normalizing. If you rescale the rewards so that the very most any policy will give you, no matter the action you take, is just a reward of size 1, and at the very least is 0, then suddenly extreme situations like this become useless, even though there is a very long loop and you can continually rack up rewards. It doesn't get you that far because your rewards have been scaled down low enough. Now, instead of the extreme values of rewards being what dominates, it's just the probabilities that dominate. The most likely utility functions will be the most likely to be optimized, or the Bayesian mixture is governed by probabilities, and if there's a lot of very likely utility functions, then a rough sum of those will be what's maximized. But there's another problem. What happens if the true value function is incredibly unlikely? Well, for example, this might occur through some fairly simple situations. AIU has a sensible prior. It penalizes complexity and places low probability on very complex situations. But a human comes up and tells you, okay, human value is fragile and extremely complex. Then that means that your prior will naturally result in a very low probability for the true reward function. What can AIU possibly do? Well, if we go back to the example of the maze, then what you might try is maximizing the minimum value that maximizing the minimum reward you expect you will possibly get. So for example, say you think that it is overwhelmingly likely to be the case that your creator wants you to stand by doors, but you suspect that if you don't stand by any red things, then the whole situation will collapse for humans. It will become something undesirable. So you anticipate, okay, I should try and alternate a little between the two, try and give some resources over to the very unlikely stay by a red thing. This way, both cases are covered and both cases will get some value, and it may be that humans would be willing to accept this. Like a more plausible example is, say, you are existing in a world where there's a trade-off between freedom and happiness. If you optimize solely for freedom or solely for happiness, then that's probably going to break things very, very badly. You could either be completely free, perhaps say, I don't know, a series of dictators or some hyper-capitalist economy with some very strange dynamics, or you could just be wire-headed and just your brain flooded with endorphins. Both of those cases are obviously breakdowns that a human would say, yes, that's just horrible. And if you ensure that rather than maximizing only one thing, you maximize some mixture, you ensure there's some base level of resources dedicated to either, then it's less likely human values will collapse. But in general, it's not so easy to come up with a method that deals with the true value function being very unlikely. This is an open problem, according to Stewart, and he says that it's quite an important one. All right. So we will switch over to another situation now where we'll see that there's still Goodhart-like behavior, but in some cases it's not so bad. In other cases, it's quite terrible. So for example, say you have a small cleaning robot that can move between squares. It's rewarded for going to the left or to the right. Like the maze, the two reward functions that are possible are mutually exclusive. That is to say, if you go to the left, one utility function will give you some reward, but the other will not. However, Stewart adds something to this, and you get the second figure. Essentially, here he said that if your creator is a left maximizer, they'll give you utility 1 for every time you are on the left square, utility 0.7 every time you're on the bottom left, and utility 0.5 every time you're on the bottom right. If your creator is a right maximizer, the opposite applies. So in this instance, there is a trade-off. The reward functions are not mutually exclusive. If you go to LR or RL, you can ensure that both utility functions, your creator is sure to get some value out of this. In this case, the optimal move for an agent is to move to LR or RL, depending on whichever utility function it thinks is more likely. This is certainly Goodhart-like behavior. You are stuck doing one thing forever. It's very pushed to the limits, but it's not such a bad option. All utility functions get something. There's not really much perverse incentives, etc. It's a relatively okay situation. In the second figure, however, we add two more squares that can give rewards. However, there's a negative trade-off. A left maximizer will give you 1.5 utility if you go to L minus R, and it will give you utility minus 0.1 if you go to R minus L. The opposite is true for a right maximizer. In this case, the optimal Bayesian move is go to L minus R and stay there forever. That's quite Goodhart-like behavior, and we might view this as bad because there's a distinct likelihood for the right maximizer to just be suffering for eternity as the robot is stuck cleaning that square. This shows us that in general, positive, well, not in general, but we might generalize this to positive trade-offs partly helping with Goodhart-like behavior. It it reduces the sting of it. Negative trade-offs, however, make things worse. And Stewart generalizes this a little by looking at the shape of Pareto frontiers. So a Pareto frontier is defined as you have some resources that you can allocate towards certain actions. Like say you have, I don't know, a number of paper clips you can produce on the x-axis and a number of pins you can produce on the y-axis. And there's a bunch of people with different utility functions saying, oh, I want you to make pins, I want you to make paper clips with such and such in such and such numbers or in such and such ratio. A particular use of resources is called Pareto optimal if there is no way to shift around the resources that could improve things for one agent and not ruin things for other agents. So every single point on these lines that you see in these graphs are different Pareto optimal scenarios. If you try to move to another point on another line, then there is nowhere you can move to that would make everyone happy. Now, there's obviously a few different graphs here, and the shape of the graphs is quite important. The left graph is quite nicely rounded, it's convex, and in it, any assignation of resources that's Pareto optimal is going to have a little bit of something for every utility function. You can just see by the shape of the curve that it's quite far from the origin. At any point, there are a fair bit of resources being used for each utility function. However, because it's curved, what that means is that, say, if you decrease the number of paper clips you have over here, say this is pins. So say you decrease the number of pins by some amount, then you will decrease the number of paper clips by quite a large number. Sorry, you'll increase the number of paper clips for quite a large number. So for a lot of agents, it's quite likely that you'll be producing a lot of value because you're only reducing the number of pins a little, but you're gaining quite a substantial degree of paper clips. Sorry, that's even more than I thought. However, as you go further and further and further, eventually you hit a point where you no longer get much of a return by decreasing the number of pins and turning it into more paper clips. So eventually most of the utility functions you encounter are going to be contributing something in pins and something in paper clips, and there's no scenarios where you will just focus solely on paper clips and just keep unboundedly increasing the number of paper clips or the number of pins. This is different in the case of a flat Pareto boundary. In this case, you can trade off the number of paper clips you produce for some number of pins, no matter where you are. And say if you start out here, then any other point is just as likely. So the extreme points satisfies as many utility functions as basically any other. And the extreme utility functions become substantially more likely to be optimized by an AI, by AIU. If the frontier is curved inwards or it's concave, then in this case, extreme values tend to be preferred because you can keep, for a small decrease in the number of paper clips, say, here, you get a larger increase in the number of pins, and you can constantly do this and just drive things up more and more and more until eventually you have a huge number of pins. Everything is just turning into pins and there's no paper clips. And that's quite an extreme scenario, which generally you don't like. That's a very classic case of Goodhart-like behavior. So we see that we might generalize the earlier comments about positive and negative trade-offs in terms of the shape of Pareto frontiers in more general scenarios. And we can use that as a criterion to check whether or not we expect to encounter substantial Goodhart-like problems. And I believe that's it. I am terribly sorry for explaining all of that so badly. But if you have any questions, then I will endeavor to answer them.
I think you explained things very, very well.